So once again, the input stage, we have many missing data. So the original, so input wise, it is the how to fill out the missing information is undefined for the SVD. So the easiest way is we replace the missing values with the zeros or the average rating values. Otherwise, we can develop the alternative, the optimization objective function. And this is based on the reconstruction error, but only over non-entries. But with this optimization, we can predict the new rating for the INJ. So we try to optimize this objective function to minimize these sum, and we can have these U vector and V in J vector. And as soon as we get this one, after finishing the optimization, and we can produce the ratings with this computation. We can visualize the result in the same way as like this. So any questions about the traditional approach? Let me know. So in this lecture, we will cover the recent trend as well. So like the other domain, other application, neural network is also dominant in the recommendation scenarios. The GNN is popular even for recommendation because as you saw in the beginning, so observation around the users and items could be formulated with the graph representation. So we can utilize the graph neural network as an idea, and we can develop another the new version of GNN, particularly for the recommendation. It could be categorized into two different types. First one is general recommendation. It is purely from the user item interaction, or at the same time we can leverage social network and knowledge graph. So we will introduce more about this. And we can utilize sequential information and with the sequence, and it could be enhanced by the social network and knowledge graph. And the sequential recommendation is also recently people defined the session. Session means depending on the temporal interest. So when you buy some product, you have a very specific the product need, right? When you purchase the textbook, you just compare the prices or the used book or new items, and you have specific need. When you finish the shopping or the textbook, and you take a 30 minutes break, and you come back to the coupon once again to buy some t-shirts, right? So this must depend. So the session is defined by the individual, the product need. So usually we divide the session by the break, or when you're shopping, it's done, you take a break and we go to another place or visit another website, right? And then come back once again and densely interact with the coupon and Amazon. So your new session is started. And so depending on the session, your need and recommendation, it should be different. So this is called session-based recommendation, is part of the sequential recommendation. So we will give you the recent ideas about those categories. So we came back to user item interaction information. So the first category, general recommendation, aims to model user preference by leveraging user item interaction data and provide a list of recommendations reflecting the static long-term interests of the user. The key challenge is how to propagate the information of interactive items and users to the user item and learn final and user item representation for prediction. So here we have, we can divide the challenge into several items. So first one is propagate. So we have the bipartite information, and the key idea of the recommendation is based on the observation we identify the user's preference in the items sort of categories and in their semantic representation, and based on these informations we recommend items, right? So to do that, we propagate information to the item. What the propagation means here. So to decide the user's preference or user's representation, we need to give the item-wise information to decide user's preference. Because in the observation level data, this user purchased these two items, and based on this, the user's preference could be determined. What about the connected other user? So this user is purchased item in this item and this item as well. But these two users are shared these two items, but this item is different. This could be indirectly related to this user. We need to propagate along with the graph data. So this item is 1, 2, 3 hops away. So we propagate this information and by 1, 2, 3 jump in this graph. So that's what we say propagate information here. And so these are based on the deep neural network based approach, and we need to decide the user item representation using vector. So actually, the final the prediction stage is very similar to the traditional approach, right? So latent vector in the matrix factorization. So we have users and items representations with the approach, and when they are similar, we recommend the item. So the similar means we have the highest score when we multiply those items. So we need to have the representation, even in the deep learning based recommendation model. And we need to develop how to do that. So that is the key challenge in the deep learning based user item interaction information based recommendation. So we specify the more details in the problem. So first, As we shown in the beginning, we can imagine many different variation of the graph data. The obviously original bipartite graph is composed of item user interactions. Maybe we can create another edge to the two hop neighbors. In the previous example, based on, so even though these items are not connected in the beginning, so we can create the edge, right, to consider the similar users. So these are the example of the graph construction. And when you have a very dense data, when you deal with the billions of users and billions of items, and difficult to deal with all the interactions to learn the model, so you need to sample the representative neighbors for graph propagation. But you should maintain the similar performance. So that is the first issue. The second issue is neighbor aggregation. So I told you the propagation is important, and aggregation is a specific way to gather the propagated information. So we discussed this in the previous GNN classes, right? And we need to decide whether differentiate the importance of neighbors or just use affinity, or can we consider interactions among neighbors? These are issues we have. This could be seen as the model choice. Third issue is information update. How would you update? How could you update and to decide final representation of the users and even for the neighbors? The final issue is the final load representation. So you're likely to have the deep layers, but need several layers to decide the user and item representations, and we need to utilize all the information to get the final load representation. Could be different from the computing the internal representation, because this will be directly used for the rating predictions or the edge prediction. So it could be different from the previous issues. So this is a general framework. And the most of the neural network based recommender system follows this framework. We have set up users, and we have set up items as input, and we have interactions. It is defined by interaction between user and I, bipartite graph. At first, we construct graph or construct subgraph GUI by sampling. So here we decide two kinds of representations. First one is neighbor representation, and to decide neighbor, First we get neighboring node information. So here we give you the information. So this is the bipartite graph. So when we take the neighboring node, so assume that u is 1, and the neighbor is it is connected to the I2, right? So I is so in U is composed of just one node, something like that. So it gives you the neighboring node information and aggregate the representation. So what is the example of aggregation? So as you know, we learned the example in the previous GNN lecture, right? We can just compute the mean or just multiply by two-dimensional matrix and go through the nonlinear layer, so you can decide neighboring node representation. So this is about your neighbor and your neighbor in U, right? So anyway, you decided the representation, and then it updates toward the final, not final, the temporal representation. So this iterate till the Lth layer. So which means, so L start with the 1, 2, blah, 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 to the L equals to large L, right? With respect to the every U, we give the U, we decide the temporal H U 1. And this goes to the HU L plus 1 because it is updated toward us, right? With this way, representation of U went up, and now we have representation from each layer. Oh, it started from the 0, so it starts from 0, right? Oh, 0 should be the just input feature. Anyway, so we have here we have L plus 1 representation, right? The per node. So from the 1 to the L is from your network. The 0 is from the input feature about the user, right? So the user's the input profile information could be given. So this represents final user representation, and we also have final item representation. We also have one L plus 1 representations. So these are engineering framework. With this way, we need to develop the function and how to decide the real final representation using this input. The easiest way is just concatenate everything, or we just get the mean pooling or max pooling, or you can connect to the another fully connected layer to reduce the dimensionality and decide the final representation, and it's up to you, and we will give you the examples about this. So anyway, this is a generic framework for recommended system from the recent observations. So these are returned the best result and this is the state of the art. So let's look at one by one. So in the previous generic framework, we need to construct the graph data. How to do that? So in addition to the bipartite graph data, recently people try to think about how to add another useful edges or useful nodes. There were two examples. So first one is, so these are the two that add edges between two hub neighbors on the original graph to obtain user and item graph. So just add edges the two hub neighbors. Now these are returned the best result, a meaningful result. What about others? So the PinSage, this is presented in the KDD 2018. It gives you the random walk-based sampling method to obtain the sample graph. So like I said, the generic graph, we can construct the subgraph by sampling when you have a very big graph. So we sample the partial observation from the input graph, and it considers fixed size of neighborhood. And from the sampled graph, we use graph neural network and decide final representation. What about the IZMC? So it uses target user item and their one hop neighbors as nodes to construct a subgraph. The subgraph design reduces dependence on the original structure. So sampling always has the trade-off between the original graph and computation efficiency, right? So we lose the original information. So you need to choose the sampling strategy and very carefully. So here the second method, construct a subgraph. So this is different from sampling.